All right. Hi, everybody.
Hi, Dr.
We are gonna crank through this last section for test 6 content here. I have a little other test 6 like review stuff that we'll do next week, but this is the last topic. Everybody cool? Okay. How many of us are in physics or have been in physics?
6,
Okay.
7.
In this section, we're going to be talking specifically about work. In physics, work is force times distance, right? Assuming that your force is constant. What happens if force is inconstant? Then we have a problem, right? So what we're going to do is we're going to take infinitely many instants, find the force at that instant, multiply it by the distance covering that instant, and add up all those little mini works to get our whole. What does it sound like we're doing here?
Riemann sum.
A Riemann sum, which means that what this is going to turn into is just a integration problem. Everybody's okay with that plan? Does that make sense as to what I'm describing? This idea of like, oh no, it should be this times this, but one of the things is not constant across the whole way. How do we deal with this? It's the same way every time we treat it as like an integral, right? We just take little tiny slices and we find, and then eventually infinitely tiny slices, and we add them all up, and that's just our integral. So let's look at an example. So example part A. This is a physics problem, like from your non-calculus based physics class. It says how much work is done lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high. Use the fact that acceleration due to gravity is 9.8 meters per second.
What is G?
That's the force due to gravity. The acceleration due to gravity is G. So we know force is mass times acceleration. Right? And we know work is force times distance.
I see where this is going.
And then you're done, right? And then I think work is joules is the unit, whatever that comes out to be. Everybody's okay? Physics students, what is the force in this problem? In part B, it says how much work is done lifting a 20-pound weight 6 feet off the ground?
The applied force of the person?
We don't know. Yeah. We don't know because we don't know the force pull.
You're all wrong.
Oh, awesome.
It's
Nope.
infinitely.
In physics, what's the difference between weight and mass?
Your mass is constant.
Weight is a force. Mass is a
Constant.
like a quantity, right?
Yeah.
So you have a 10-pound weight.
F grab.
What is the force?
F grab.
With a 10-pound. That's pretty bad.
10-pound
Oh,
weight.
60. Oh, 100.
No.
Force is 20 pounds.
200.
The force is 20 pounds.
2.
Because a weight is a force.
Oh my God.
That's it. That's your force.
Force is 20 pounds.
Yeah, I wasn't gonna.
The force is 20 pounds. Weights are forces.
So weight is.
The work was more.
So the work is 120 foot-pounds.
Mark, you don't.
Does Is that okay?
I can't see that.
All right. But what if the force isn't constant? What are we going to do? We're going to do an integral.
That's what we're gonna do.
Okay? So, example 2 says, when a particle is located x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is done moving it from x equals 1 to x equals 3? That's it. Yeah. This is force times distance, where the distance is just like an infinite little sliver. That's the dx. And that we're slivering from 1 to 3. That's it. Does that feel okay? I'm not going to do the computation because we're over time with what I planned. So I'm just going to kind of skate through some of these things that, like, the integral should be easy and we can do this, I would hope, with a great deal of accuracy at this point, right?
Yeah.
Doing polynomial should be piece of cake, right?
Yeah.
Yes. All right. You guys talk about springs in physics?
Yeah.
Okay. So Hooke's law describes the forces or the interaction of springs. Hooke's law says the force required to maintain a spring stretched x units beyond its natural length is proportional to x, i.e., that force is equal to k times x. Where k we refer to as the spring constant. So example 3 is going to be using Hooke's law. It says a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. What is that first sentence going to be used to do?
Figure out the mass. And the force.
I'm going to have to find k.
I think we're not even in physics.
It's not 8, unfortunately. No, units matter here.
Oh.
What did they do that's crummy for us? Centimeters. What unit does that need to be in?
Meters.
Meters. Ugh.
Why so many meters? Where else does it say meters?
0.01.
A newton is a
No, there's not.
meter.
Kilogram meters squared.
Yeah, something like meters per second squared. Yes, kilogram meters per second squared is a newton.
Oh.
Yeah,
Time to do some conversion.
so it's hidden in there for you.
You should teach it.
I should teach physics. I don't know if you really want that to happen. Don't you have enough of me? So like K is 800, I think, then,
3
right?
classes, Dr. Cool. You got 3 classes again.
All right. How much work is done then stretching the spring from 15 to 18?
3? That's the difference.
0.03 times 800.
Right? It's 800x times dx, right? Force times distance. I guess we'll have to finish this next time. That's fine.
What is the unknown like what is making it into the interval and not like the previous example?
Because the force is changing depending on how far the spring is stretched. The farther you stretch it, the harder it is to pull.
So the force is always changing. Why?
No. Well, I mean, it's 800x, but
Yeah, but that's why it's not.
the force is not constant.